And whether the screen is visible or not, can you please confirm? Okay. I hope the screen is visible. Just check 1 second. Okay, it seems it's fine. Uh, Good evening, everyone. Myself, Arka, and I'm working as a Prime Minister's Research Fellow in the Department of Electrical Engineering, IIT Patna. And I will be your NPTEL PMRF TA for this course on discrete time signal processing. This course is offered by Professor Mrityunjay Chakravarti, who is a professor in the Department of Electronics and Communication Engineering, IIT Kanpur. So let's move to the presentation layout for this particular week. So in this live session, so we'll start with solving the week 5 quiz. Then we'll see the quick recap of the week 6 content. So in week 6, the main theme is basically the filter design or the introduction to filters, introduction to filters. Okay, I guess someone is joining. So in this week, the main theme was introduction to filters, which basically comprises IIR filter, that is infinite impulse response filters, and the FIR filters, or called the finite impulse response filters. Then we'll see the properties of these filters and different structures, different filter structures for representing these filters so that we can deploy the filters in the hardware. And thereafter we'll solve some questions which are related to week 6. And then we'll have some short Q&A session regarding if you have any query regarding week 5 quiz or the questions which are related to week 6 that will be covered in this particular live session. So moving forward to the quiz 5. In quiz 5, the main topic was the multi-rate signal processing, and here the topics were the decimation followed by interpolation and the Nobel identities to some extent. However, mostly the questions that I have seen basically framed on the basis of decimation and interpolation, these two techniques, or the upsampling, downsampling. So the upsampling, downsampling, decimation, interpolation, and novel identities. So let's start solving the questions. So this is the first question of week 1. So we have been given the cascaded form of two they are working basically in parallel. There are two systems. One is the downsampling system, followed by there is an upsampling system, and thereafter we have some delay. And here the same thing is there. However, the delay is applied first, and then followed by the delay we have the downsampler, followed by that we have an upsampler. And we need to find the output yn, which is summation of these two paths output. So we need to find what is the relation of yn with xn, or how the yn is related with xn. That is the main question. So for these kind of questions, what we have to do is basically let's take points over here. For each of the block, we'll take an output. Let us consider this is y a of n, this is y b of n, this is y c of n, Similarly, this is while d of n and y f of n. So by this diagram itself, we can just readily comment that y of n is equals to y cn. So this is y cn plus y f of n. So this is the equation and we need to evaluate what is YCN and YFN respectively. So let's start evaluating these particular relations. So we'll start with what is YAN. Let me just change the color. So let's start with XN. XN has following components. For example, X0, X1, X2, X3, X4, X5, X6 and dot dot. And in the negative side also, so we have x of -1, x of -2, x of -3, x of -4, x of -5, and x of -6. And this is the starting point, which I have indicated with this arrow. So this is the starting point, and this is the right hand side part, and this is the left hand side. Now we need to find what is YAN. YAN. So YAN, what it is mean? It is basically downsampling the signal by a factor of 2. Therefore, we can take the samples. We can drop the samples. Actually, we can drop the samples in a regular interval with a factor of 2. So therefore, the first sample will be x naught itself. The second sample will be x of 2, as because we are dropping the samples with a regular interval of 2. Thereby, we'll take the sample which is basically coming at the position 2 over here. That will come to position 1 in the YAN. Thereafter, we can take x of 4, then x of 6, and dot dot. And in the negative side also, likewise, I can write it as x of -2, x of -4, x of -6, and dot dot. And this is the starting point, or this is the origin. Now, followed by that, there is a upsampler. Upsampler, what it basically does, actually, it injects some zeros, m minus 1 0. For example, this is upsampled by n, so it will inject m minus 1 zeros in between two samples. That is what we have seen in the last live session also, or in week 5 content also. It is very elaborately, it has been described. So how the upsampler, downsampler works. So it will start with x of 0, and this is the origin. And then there will be m minus 1 0. So m is basically 2 over here. So it will inject a single 0. So 0 followed by x of 2, then 0, then x of 4, then sorry, here it will be 0. So 0, x of 6, and dot dot. And similarly, in the left hand side, it will be x of -2, 0, x of -4, 0, x of -6, and dot dot. So we have got what is yn, and yc of n is basically we are delay by 1. There is a delay by 1. So delay means x naught will go to the first position and x0 will come at the origin. So it will look like. So delay means it will be shifted by 1 in the right hand side. Therefore, 0 will come over here. X naught will be shifted over here, and then as it is, whatever values are there, I'm just writing the values. 0, x of 4, 0, x of 6, and dot dot. And in the negative half side also, it will be just x of -2, 0, 0. Sorry, it is single 0, 0. And then again, x of -4, 0, and all. Now mind it, as because 0 has been shifted to the origin, now this is the location of origin. So this is the yn signal. Simultaneously, for this particular path, we have reached to YCN. Uh, Now we have to see what is YFN. So let us proceed through this particular branch. So the first output is basically the YDN. So let me write what is YDN. So YDN is basically the shifted version of X of n with a delay or with a right shift of 1. So therefore X naught will go to the first index in case of YDN. So I can write it as X of -1 followed by X of 0, X of 1, X of 2, X of 3 dot dot, then X of -2. So -3, and in the right hand side also it will go like this. Now mind it, as because this has been shifted by 1. Now at the origin, the sample is X of -1 instead of X of 0, as because it has been shifted in the right hand side by a unit shift. Followed by that, we need to write YE of n. Now YE of n is basically the downsample version. So downsample version means we'll be dropping the samples in a regular interval. So this is the zeroth location, first and second. So therefore, the next component will be X of 1, then 3, 4. So fourth component is X of 3 and dot dot. And in the negative side also, I can write it as X of -3, -4, -5, X of -5, and dot dot. Thereafter, we have upsampler. So upsampler, as already we have told that upsampler basically injects n-1 zeros in between two samples. So it will be just like X of -1, 0, X of 1, 0, X of 3, 0, X of -3, 0, X of -5, and likewise. So now we need to add by f of n and by c of n. So let's just write yc of n just below the yf of n for better clarity. So it is 0 followed by this is X naught, 0, X of 2, 0, X of 4, and in the negative side it is 0. Oh, sorry, this is X of -2. So this is X of -2, 0, then X of -4, 0, and like this. So I have just retained this part over here. So this is what YCN looks like. I have just retained YCN over here. So now if I add these two signals, so it will result in X of -1, X of 0, X of 1, 2, 3, and then it will be X of -2, X of -4. Sorry, it will be X of -3. It will be X of -3, X of -4, and so here the origin in the origin the sample value is basically X of -1. So thereby we can observe that this was Xn and this is your Yn. So Yn, we can observe that from these two sequences, Xn, if we shift Xn by a shift of 1, so we'll get this particular sequence. Therefore, I can write it as Yn is equals to X of n-1. That means the output Yn is basically a shifted version of X of n, and that shift is basically by a single unit. Therefore, option D is basically the correct answer for this particular question. Okay, so moving towards the next question. So in the next question, we have been given a system. So the system is nothing but a upsampling system or an upsampler. So given this upsampler, we need to find whether the system is linear or not and shift invariant or not. So let us just write the governing equation for this particular system. So we know for an upsampler, yn output is related with input in this particular fashion. So x of n divided by m, where n by m should be integer and 0 elsewhere. And by n by m should be integer, I mean n by m should be integer, which means that n should be multiple of m. So plus minus m, plus minus 2m, plus minus 3m, like that. So only if n is retaining these particular values, then only this factor will be an integer. So this factor will be an integer only if n contains these particular values. And for all other locations, it will basically give you 0. So that is what the upsampler does. It injects some zeros in between two samples. Now, for checking whether the system is linear or not, we need to take two particular signals. So let us consider x1 of n. So if I feed x1 of n into the system, so I will get y1 of n, which is basically related as x1 n upon n 0, and the uh, conditions are just same as the earlier one. So n by m should be integer and 0 elsewhere. Similarly, x2 of n is basically y2n with x2n upon m. N by m should be integer and 0 elsewhere. Now let us consider we are actually applying some combination of linear combination of the inputs, therefore C1 x1n and C2 x2n. So at that time, the output, let us consider that is y hat of n. So that y hat of n will be C1 x1 n upon m plus C2, sorry, C2 x2 n upon m. And the condition is just the same. Only n upon m should be integer and 0 elsewhere. So y hat of n, I can see that it is basically C1 y1n and C2 y2n and 0. This is elsewhere. And here it is the same condition, n by m is integer. That means y total n is basically the linear combination of the outputs y1n and y2n. So we are seeing that there is a linear combination of the outputs when the inputs were applied separately. So that means the particular system obeys the superposition theorem. Superposition theorem. So as because the system obeys superposition theorem, so we can comment that the system is a linear system. So first part is done. So we have proved that the system is linear system. Now what we have to do is that we have to check whether the system is shift invariant or not. So let me just create some space for this. So we need to check whether the system is shift invariant or not. To understand whether the systems are shift invariant or not. So we'll start by getting some examples, some value-based examples. So let us consider we have a signal. We have a signal input signal x of n, which has this particular shape. So 0, 1, 2, 3, 2. And the amplitudes are 1, 2, 3, 4, and 5. Maybe someone is trying to show me. So over here, we can see that the signal x of n has this particular shape. Pardon my drawing because 3 and 4 they are having almost the same amplitude level, or let me just fix it. So
power on. You've plugged into Nirvana. Your device is ready to pair.
I guess. Okay, so this is what xn looks like. Now, given this particular xn, let us consider we are feeding this thing into the upsampler system and we'll get some output over here. So the output basically, let us consider this is a factor of m is equals to 2. So we'll be upsampling by a factor of 2, or let us consider for a generalized case. So we'll consider m1. So with m upsampling, it means that it will inject m minus 1 zeros in between two samples. So let me just get another page and copy this part of the file. So if I use an upsampler for this particular case, I will get something like this. The zeroth. So at the zeroth location, the value will be same. This is 1. And there will be n minus 1 zeros. M minus 1 zeros. So at mth location, I will get the second value at mth location. Then again m minus 1 zeros, m minus 1 zeros, and at 2m location, I will get the third output. And likewise, let us consider again m minus 1 zeros, and at 3m, I will get this particular output. And again m minus 1 zeros, and at 4m, I will get the next output. And let us consider there are some samples in the negative half also. I'm not drawing the negative half samples. You can just employ any negative half samples and you can experiment with that also. So this is what if you give x of n, so this will be typically your y of n. Now let us consider you are shifting the signal by an amount of 1. So if you shift the signal by an amount of 1, now the signal will look like, let us consider at -1 the receive. So here it will look like -1th sample will come to 0, and then it will follow the next. So this is 0, this is 1, 2, 3, 4, 5. So eventually the fourth sample will go to the 5th index location. So this will be 5, 4, 3, 2, 1. Now you provide this thing to this particular upsampler, and let us see what is the output for this particular system. So original samples, let me just plot it with the same color. So this is the 0th location. At 0th location, I will get the same value as 0. Then at mth location, I will get 1, 2m. So it will be 2, 3m, it will be 3, 4m, and at 5m, because let us consider it's 5. And in between, there will be what? M minus 1 zeros. So it will be n minus 1 zeros, 1 zeros. Now this is when you delay the input, delay the input, and then you get the output. Let us consider this is y2 of n and this is y1 of n. So when input you have given as a delayed format, so you are getting y2 of n. Now you in this particular initially you had given xn itself, and this is what you have got y1n. And let's just delay the y1n as it is with the same amount. So y1 n minus 1. So y1 n1 n minus 1 it will look like, so at 0 let us consider there is nothing, so the 0th sample will go to first, then we have m minus 1 0, then it will shift to m plus 1, then 2m plus 1, then 3m plus 1, and 4m plus 1. So this is 1, 2, 3, 4, 5, and in between just the same thing. So m minus 1 zeros, m minus 1 zeros, minus 1 zeros, minus 1 zeros. So that means if we just compare this y2n and this y1 n minus 1, so we can see these two signals are different, as because their index location or where the value is operating, that location is different. So therefore, we can say that y2n is not equals to y1 n minus 1. So therefore, the system is shift variant, or we can say not shifting variant. So therefore, the system is linear but not shifting. So this is the answer, linear but not shifting. So moving forward with the next particular question, this question is very easy. So the question states that we have a following system which has this kind of structure. So downsampler of 4 followed by a delay of 2. So this is delay of 2. So this is z to the power minus 200. It seems like I have written z to the power 2. So there is a minus sign. And this is a down sampler with a factor of m is equals to 4. So I can, the question states that this is 3a, figure 3a, and figure 3 is related with which of these figures? So whether it is related with or it is equivalent to figure 3b, 3c, or 3d. So let me just use some properties that we have studied in the course. So this is 4, and I can write this z to the power minus 2 as a cascade of z to the power minus 1 and z to the power minus 1. That means just delay single unit delay. So cascade of single unit delays will give you z to the power minus 2 or delay of 2 unit. Now, associated with this, there are some identities, structural identities are there, which are called noble identities. So there are two kind of noble identities that we can actually observe. So these noble identities have a particular relational mapping. So this relational mapping we can get it from here. Let's say you have an xn, x of n, and let us consider you have a downsampler with a factor of m followed by h of z followed by a filter, just a filter response, and you are getting y of n. So it is equivalent to, if I have to take this filter in the first location, so what I have to do is that I just need to take a power of it. So z power m, and then I can write it as downsampler of M followed by the amplitude. So this is the output and this is the input. So in this way, the noble identity relationship holds. So by this logic, if I use this particular operation over here, so I can see that there is a downsampler followed by a filter. So delay, we can consider it as also a filter, or any transfer function representation is there. So this transfer function is basically 1 upon C. So I need to take back this z to the power -1 into the first location. So if I have to do that, what I need to employ, so z to the power -1 to the power. So it will be z power m. So it will be 4. And then, sorry, then there will be the downsampler. And this is 1000 by 1. So it will look like z to the power -4, downsampler of 4. And then we have z to the power -1. So by this logic, option D is the correct answer. So option D 3A. So figure 3A is equivalent to figure 3D. So apparently it will be option C, as because system shown, the system shown in figure 3 is equivalent to system shown in figure 3D. So your option will be C, option C. And figure D, option C, figure D. Okay. So moving forward with the next question. The next question states that we have a system over here. So the system has a cascaded version of one downsampler followed by an upsampler. So this is what we have downsampler, and here we have an upsampler. And we need to find that what is the relationship between yn and xn, or how yn is basically related with xn given this particular system. So we need to, we have seen in the last week's live session also, we had studied some problems related to these particular structures. So what we have to do initially, we have to get the output at each point. So we need to find what is y(a) of n and y(b) of n. And effectively y(b) of n is your yn. So we need to find these two sequences, and we need to also consider that what are the locations at which we'll get the samples, as because there is an upsampling process involved with this particular system. So upsampler, what it does, it injects some signals. So we'll not get values at every point. So we have to make sure that at what index we have to choose, so that we can get the what you call the samples. So sample location is very much important for these particular options. So let us start with what is y(a) of n. So y(a) of n, I can write it as because it's a downsampler, so it could be x of n into L. So here I don't have to bother about the sample locations, as because in downsampler what will happen is that I'm dropping some samples from the original signal in an regular interval. So therefore yn is equals to x of nl, and nl should be an integer. So that is quite trivial. So second one is that yb of n. Here actually the main catch lies. So yb of n, I can write it as ya n upon L. So this n upon L is basically the main governing point at which location I will get the values. So n upon L should be integer. That means n should be multiple of L. So plus minus L followed by plus minus 2L plus minus 3L, etc. So YB of n is equals to YA n by L with this particular relation, and y a n by L I can evaluate using the equation 1. So let us consider this equation 2. I am using the relation of equation 2 and equation 1. So y a is basically x of nl. So it will be x of nl by L. So it is effectively x of n by b of n. But we have to mind it. We have to consider that n by L is integer. So your final yn is equals to yp of n is xn with n by L integer and 0 elsewhere. So let me see what are the options. So many people does uh, choose this particular option, yn is equals to xn. So the common logic they find that, okay, we have a downsampler followed by upsampler, they will cancel the effect of each other and then we'll get yn is equals to x of n. So that is a very wrong concept. So we need to basically consider that at what location the samples values will exist. So option A is incorrect. Then what about option B? Yn is equals to x of n, and provided n by L is an integer. So final answer is option B. So Yn is equals to uh, x of n and n by L is an integer. And this particular option is just giving you the output over here by an, and this one is x of n by L. So the argument inside x is incorrect. So therefore option D is also nullified. So option B is the correct answer. Okay, so let's move to the last question. So this is the final question for this particular week 5 quiz. So we have been given a system. So this is the particular system, and there are some relations have been given. So h of n is 2 comma minus 1, and 2 is basically the location at relation. And g of n is equals to h of minus n. That means there is a time reversal process associated with that. So whatever signal is there in the h of n signal, so all the components will be time reverse about the y-axis. Therefore, I can write it as -1 followed by 2, and 2 is the origin location. Now we need to find what is g of n minus 1. That means there is a delay associated with that. So delay associated with that will result in -1, 2. Now this was at -1th index, and this was at 0th index. Now as because I'm shifting this particular signal with an amount of 1, therefore the origin will contain -1, and at the first location the signal value will be 2. So I can write it in the form of the delta function. It will look like delta n and then 2 of delta n minus 1. Now let's solve this particular system. So here also in these questions in upsampler, downsampler, these particular questions you should care about the outputs at each point. So at YA, then YP, C, and finally YT of n. So effectively YT of n is equals to YN. So I just have written for the continuity. So I can write YAN is basically a convolution between xn and g of n minus 1. So xn convolved with minus delta n plus 2 into delta n minus 1. So we know if we convolve any signal with the delta n, we'll get the same signal. So minus x of n. And if we convolve the signal with a shifted delta, so we'll get the shifted signal. So plus 2 into x of n minus 1. So this is what YAN looks like. Now YB of n. So YB of n is basically a downsampling version of YA. So I can write it as YA 2n, and therefore let me just use the relation that we have found in equation 1. So it will just be x of 2n. In place of n, I am just putting 2n, and then 2 of x of 2n minus 1. Okay. Thereafter, we need to find what is YC of n. So YC of n, we can see there is an upsampler associated with that. So for an upsampling operation, we know that YP n upon 2 and 0. N upon 2 is integer, and this is elsewhere. So using that particular relation that we have found in equation 2, we can say that it would be minus x of n plus 2 into x of n minus 1, as because I'm just putting n by 2 in place of n. So it will be n by 2 integer, and elsewhere I will get 0. So this is what, oh, I'm sorry. So this is what YCN looks like. So the last operation is YDN, which is equivalent to YN, and this is a convolution between HN and YCN. So we need to use the convolution operation in between these two particular sequences, what is HN and what is YCN. So one may think that, okay, I have got some equation, some relation between YCN and X of n. So I will use this particular relation to use the convolution operation. So this is where people makes the mistake. In each and every point, I am not getting the same value. In some places I have 0, in some places I have X of this particular representation. So for these kind of questions, we need to go for uh, graphical approach of convolution. So let's just copy these equations, and then I will first try to draw this signal itself, what is YCN and what is H of n, and then we'll do the convolution directly. So these are the equations that we need. So let's start drawing the sequences. So n by 2 integer, it means that n should be 0, plus minus 2, plus minus 4, likewise. So we'll start from 0th location. At 0th location, what we'll get is that minus x of 0 plus 2 into x of minus 1. Then at first location, I will get 0 only. Then at second location, I will get some value. At third location, I will get 0. At fourth location, I will get some value. So at third, I will get 0, and at fourth one, I will get the I will get some value over here. So at fourth location, the output will be minus x of 4 plus 2 into x of 3. So this we can call it as, and let me just write the convolution equation over here. So y n is equals to convolution between h of n and YCN. So YCR h of n minus r, and r is running from minus infinity to infinite. And in the question, they have asked to find what is y3. So let me just put the value y3. So this equation will effectively converts to h of 3 minus r, and r is minus infinite to infinite. So what is happening here? H of 3 minus r. So we have what is called h of r, which looks like uh, h of r looks like. So at 0, the amplitude is 2. At first index, the amplitude is minus 1. So here I can write it as 0 with a value of 2, and that is minus 1 at index 1. So first operation, this is h of r. Second operation, we can write this thing as h of minus r plus 3. In the first lecture itself, I had told that for this particular composite operation, we'll look the signal, we'll have look the signal from the right to left. So therefore, in the right, the operation is advancing the signal by 3. So therefore, h of r plus 3 will go to, say, minus 3, and then it will be at minus 2. The value is minus 1 and 2. And then what we have is that a time reversal operation. So time reversal operation will effectively give you 2 and minus 1, and the location will be, so so it will give you this and this. So this will be minus 1, and at second location, at third location, the value is 2. So thereby, here also I will get some value. Now this is what is, I'm sorry. So this is what is x of r looks like, or particularly YCR looks like. So this is YCR, and we need to plot h of 3 minus r. So h of 3 minus r has got values in 2 locations. So the locations are, so is over here at this particular location, it has got nothing, and here also it has 0, and at 0th location there will be no value. Followed by that, as because we can see there is a shift of, initially there is a advancing of the signal by an amount of 3. So therefore the signal was initially shifted to minus 3 and minus 2, and then we have got the what we call time reversal operation. So therefore, whatever signal is there in the time domain in, so let us consider this is with index r, and this is what is origin. This is origin, and this will just be taken to the uh, taken to the right hand side of the plane. So this is just the time reversal operation. So this will act as like a mirror, and this will be mirror image. So at 1, there is nothing. This is at 1. This is at 2. At 2, I have got some value. And then over here, at 3, I have got this particular value over here. So with this particular option, we can see, and at 4th location, we have got nothing. So is 2, 3, and 4. So therefore, we can see what I was initially telling that if we start doing the convolution with this particular representation and we employ what is h of n is as 2 into, so the representation over here is 2 into delta n and then minus of delta n minus 1. So if we have convolved with this particular sequence directly with this one, so we will get something called the wrong representation, as because at every point the value is not the original, the value is not basically the x minus x of n plus 2 into x of n minus 1. In some places we are getting zeros also. So therefore what we have to do is that, so we need to take ycr dot product 3 minus r, and r is running from minus infinity to infinite. So therefore I can write it as minus 1 into the value that is coming over here. So I can write it as x of, so this is x of minus 2, so minus x of 2, and then minus x of 2, then plus 2 into x of n minus 1. So x of n minus 1 will effectively give you 1, and then that is over here it is 2 into 0. So the value is 2 and the value is minus 1. So this will nullify to 0, and over here I will get x of 2 and then minus 2 into x of 1. So this is your final answer. So let me search for the result. So we can see that x of 2 into x of 2 into y of, so y3 is equals to x2 minus 2 into x of 1. So this is what the final answer looks like. So y3 is equals to x2 minus 2 into x of 1. So this is option 3. So with this, we have solved the questions that are there in week 5. Now let's move to the week 6 content. So in week 6, the topics are linear phase filters. So what is a linear phase filter? So why filtering operation is required, first we have to understand. So let us consider we have a frequency response which has this particular shape, let's say, and due to some noise insertion, something like this has been introduced in the spectrum. So this is due to noise, and this is a high frequency, uh, a high frequency is a high frequency component in insertion into the spectrum of the signal. So this is due to noise. Now, as because this particular region is the desired output. So we need to form some mechanism to delete these unwanted components, the red components. So for this particular option, for this particular application, we need what is called filters. Now, why linear phase filter? So linear phase filter is very much important as far as digital filtering is concerned. The digital domain filter is basically concerned. So in digital domain filter, we can broadly classify the filters in terms of their number of elements that we need to store. So we can have two types of filters as IIR, that is infinite impulse response filter, infinite impulse response filters, and FIR filters, that is called finite impulse response filters. So in case of finite impulse response filters, the number of coefficients that we need to store that is bounded. That is, for example, that will be of length n or length n plus 1. So that value that we have to store, the number of values that we have to store, that is finite. However, in case of infinite impulse response, the system response is basically dependent on the input and the past versions of input as well as the past version of output also. As because the output past version is also employed in case of IIR filters. So therefore, to get a particular value at instant n, we need to have the previous representation of x of n minus n as well as the previous representation of outputs also, which basically incurs all the insertion of infinite number of elements that we require to store for the digital domain IIR filters. So as because the output is basically dependent on the input, current input, and previous output itself. So these are called the IIR filters or infinite impulse response filters. Okay, so let me start with the derivation of the requirement why we need a linear phase filter. So to delete the high frequency components, let us consider this is well bounded between omega c and minus omega c. So effectively, we can use a box like shape, which is also bounded between minus omega c and omega c, and we can just have a dot product. So this is effectively your xc j omega, and I'm taking magnitude. So any complex number. So as because this is a DTFT is basically a complex number, as because we can see that we are having some complex exponents. So cos theta plus I j theta. So it will give rise to complex component. So complex component will have two parts. One is the magnitude part and one is the phase part. So I'm drawing the magnitude part over here only. And this is the filter response, and filter is also we are taking the DTFT. So DTFT again will have two components, phase and magnitude. So here also I'm just writing uh, the magnitude part, and the variable across the x direction is omega. Now, if we multiply these two, I will exactly get this particular shape, and these unwanted noises will be deleted. But employing just this particular magnitude spectrum means that phase corresponding to this filter is equals to 0. So that is a different class of filter that is called as zero phase filters. So we'll see why zero phase filter. Uh, what is the issue of the zero phase filter as far as signal processing is being concerned. So we'll see that in case of zero phase filter, we have non-causality operations. So non-causality operations cannot be applied into the digital signal processing, as because in case of any real-time signal, I don't know the information about the future samples given the present and past. So zero phase filter is not typically used in case of um, real-time digital signal scenario. However, in case of image processing cases, the zero phase filter can be used, as because image is a spatial data. So there is no concept of time or sample sequence. So therefore, we can use zero phase filter over there, as because time reversal is not trivial over there. So for this particular filter, if we say that this is zero phase filter, then it has some disadvantage as far as signal processing is concerned. So we need to have some uh, filter, some phase operations also. Now, what should be the phase operation? So in the heading only, we have already told that there should be a linear phase filter, and let us just prove why linear phase filter is required. So y e power j omega. Let me just draw the block diagram over here. So this is h of n, this is y of n, and this is x of n. Given this y of n is basically related with h of n star x of n, and therefore the DTFT will just be the multiplication of these two, x e power j omega and h e power j omega. So I can say that it is having two components, e j omega, h e j omega, and angle of x e j omega. So any complex number, I can write it as r into e power j theta. So by that logic, or angle of theta, so I can write it as e power angle x e j omega plus h e j omega. So this is the phase information and this is the magnitude information. Now, if I have to get y of n, I will have to take the what you call the inverse DTFT. So that is governed by this particular equation 1 upon 2 pi minus pi to pi. This will have y e power j omega e to the power plus j omega n t omega. So 1 upon 2 pi, I can just write this particular equation over here. So it will be x e j omega h e j omega mod, and then e to the power. Let us consider this particular thing is e to the power j omega k, and we are multiplying with it with j omega n t omega. And the limits are well bound between minus pi to pi, as because in the DTFT domain, the signals are periodical between minus pi to pi. So therefore 1 upon 2 pi minus pi to pi, and I can write it as x e power j omega, h e power j omega, and this will be e to the power j omega n plus k d omega. So if we compare this particular operation with the standard IDTFT equation, so we can see that the n index is basically changed by n plus k. Rest of the things are same. So I can write it as yn is equals to uh, x of, so I can have some, as because this is a magnitude part only, because it's a magnitude part only, I can write it as a x of n plus k. So yn is related with xn in a format of yn is equals to x of n plus k with multiplied with 1. So thereby we can see this particular operation will lead you to a non-causal operation. So this non-causal operation can be tackled when k is negative. So therefore, only when k is negative, I will get y of n is equals to x of n minus k multiplied with a. So this will give you some causal representation. So therefore, we need to have some linear phase with a negative value. So which will give you, which will maintain the causality. As far as signal processing is being concerned, we are more inclined towards causality and stability. So therefore, we need some causal representation to get the filters structured properly. Now we can see what is basically the zero phase filter looks like. Zero phase filter looks like. So zero phase filter means typically this will be h e power j omega. Then there will be a time reversal. Time reversal. Then we'll have again h e power j omega. And then again we'll be having time reversal. Okay, so this is x of n and this is y of n. Now, given this h e power j omega at this particular location, let us consider we are getting w of n. So w of n, we can write it as convolution between h of n and x of n. And as because we are bothered about the DTFT domain representation, we'll be converting these individual representation in the format of DTFT. So therefore I can write it as W e power j omega is equals to H e power j omega multiplied with X e power j omega. Then we have a time reversal operation. So let us consider we are getting Z of n over here. So Z of n is basically W of minus n. And let us consider Z of n. Let us consider W of x. W of n is real. So whatever output I'm getting over here, that is real. So can anyone tell me that what is the DTFT, how the DTFT looks like of an if the signal is a real signal, what is the relationship of the DTFT to the original one? So I need to find. So let us consider Wn has the DTFT W e power j omega. Now I need to find what is the DTFT of W minus n given Wn is real signal. So can anyone tell me what will be the DTFT of this particular representation W of minus n given the signal is a real signal? You can unmute yourself and just uh, tell me the answer. What will be the final result of this particular DTFT? So this thing we have seen in lecture 2. In lecture 2, we had talked about, we have solved several problems on DTFT. So let us start finding the DTFT of W of minus n. So by the definition, it will be W of minus n, then e power minus j omega n, and n is running from minus infinity to infinite. So therefore, I can change the indices or the variables, so it will be m equals to minus infinity to infinite, and then W of m followed by e to the power j omega. Now, let's say there is a real value a, and if I take conjugate of any real value, so what will be the output? If I take conjugate of any real value, what will be the output? So if I take conjugate of any real value, I will get the same result. So let us use that particular property. So let us consider this is W star of m e to the power minus j omega m, and then we are taking star over here. Now we can effectively change the location of star. So it will be W star m e to the power minus j omega m, and the star I can take outside. So the conjugation operation I'm taking outside of this particular summation. And as we know that W star n is equals to Wm, as because it's a real signal. So I can write it as m is equals to minus infinite to infinite Wm e to the power minus j omega m, and there is a star. So I can write it as the DTFT of W e power j omega, and then there is a conjugate operation, or effectively this is W star e power j omega. So at this particular location, we can see the Zn is related with the previous output in a time reversal operation. So this is a anti-causal operation. So this operation is not basically a causal operation. Specifically, it's an anti-causal operation. It will take the signals in the negative half. So therefore, these particular operations is prohibited as far as real-time signal processing is basically concerned. I cannot comment about the future samples uh, based on the present and past samples instantly. So for these operation, the zero phase filter is basically not considered in case of digital signal processing. However, in case of image processing, you can just readily use the zero phase filter operation. So in MATLAB, so the zero phase filter is basically it is the command as filt. So you can exploit this filt command to see what the zero phase filter actually does. So at this particular location, it was z of n, which was w minus n. So z e power j omega is effectively your w star e power j omega. So w star e power j omega is equals to h e power j omega, h star j omega, and x star e power j omega. Then we are multiplying or we are taking the output over here. Let us consider this is uh, P of n. So P e power j omega is basically the multiplication of the DTFTs of filter and the DTFT of Z. So it will be h e power j omega followed by x star e power j omega and a star or x star e power j omega. So it will be x star e power j omega. So let me just turn on the picture. So P power j omega is h e power j omega, x star e power j omega, and x e power j omega. So if I multiply z into z star, what I will get is mod of z star squared as per the complex signal analysis is being concerned. So x e power j omega, and I'm taking mod and then square, and then there is x star or j omega. P power j omega. After that, we have again time reversal. Time reversal means so y power j omega, it will be conjugate of this particular thing. So this is just a magnitude. So any real, so again, this is a real value one. So real value will effectively give you the same thing even after we take conjugate. So it will be h e power j omega and then square. And then we are taking conjugate of a conjugate operation. So it will just effectively give you the initial signal, initial DTFT of x e power j omega. So y e power j omega is related the input like this. So we are taking the magnitude part of the magnitude part of filter. That means phase equals to 0. Therefore, this is a zero phase filter. But only problem is that we need to do this anti-causal operation W of minus n. So this time reversal operation is not possible as far as real time digital signal processing is being concerned. But in case of image processing, as because there is no concept of time, so we can uh, anyway consider this anti-causal operation. We can readily perform that particular operation. So likewise, we have different structures of filters. So we can exploit different representation of filters, and additionally, let us consider we have an FIR filter. As because we have already said that FIR filters the number of coefficients that we have to store, that is finite. So let us consider there will be two cases. One could be the number of coefficients are odd, one could be the number of coefficients are even. So let's start with odd case. So in case of odd filter coefficients, so it will start with h0, h1, h2, dot, h of n minus 1 by 2, then minus 1, then n minus 1 by 2, and then it will start with h of n minus 1 by 2 plus 1, dot, 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 dot. Let's say h of n minus 1. So h of n minus 1 means that we have total n number of coefficients. So we use symmetricity property. How? It's like h of 0 is equals to h of n minus 1. H of 1 is basically h of n minus 2. Or I can write it as h of n minus 1 minus n 1. So likewise, that means these two are same. These two are same. So in between the following h of 1 is can be equated with h of n minus 2. So likewise, we can also infer like how h2 will be uh, inferred with h of n minus 3. I can write h of r is equals to h of n minus 1 minus r. So this is the equation. This is the generalized equation of the symmetricity property. So if I take the DTFT or if I take the Z transform, so we'll see some definite relations over there. So in case of uh, Z transform, sorry, in case of DTFT, h e power j omega, by definition, we know that it will be h of n e to the power minus j omega n, and n is running to minus infinity. So it could be written as h0 h1 minus j omega 1, h2 minus 2 j omega dot 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 dot. Then I can write it as h of n minus 1 by 2 minus 1 into e power minus j omega. So this particular location is what? This particular location is n minus 3 by 2. So if you do the calculation over here, so it will be uh, e to the power minus j omega n minus 3 divided by 2. Then h of n minus 1 by 2 e to the power minus j omega n minus 1 by 2. And then followed by that it will be n minus 1 by 2 plus 1 e to the power minus j omega n minus 1 by 2 plus 1. And likewise I will get h of n minus 1 e to the power minus j omega n minus 1. Okay, now the relation is h of 1 is equated with h of n minus 1. Similarly, h of 2 is equated with h of n minus 2, and h of n minus h of n minus 1 by 2 is equated with this particular. However, this is the only coefficient that has no relation with the other components. So therefore, I can explicitly take out this particular term out of the group. So h of n minus 1 by 2 e to the power minus j omega n minus 1 by 2. And followed by that, I can write a generalized equation which will start with 0 and which will end at this particular location, that is n minus 3 by 2. That is n minus 3 by 2. And therefore, h of r. And then I can group this operation. So it will be e to the power minus j omega r, followed by that will be e to the power minus j omega n minus r minus 1. Okay. Now, if you solve this particular equation, so let me just copy this. So this is h to the power j omega. So h of n minus 1 upon 2 equal to minus j omega n minus 1 upon 2. And we can take some representation like r equals to c to the power minus 3 by 2. So we can take some factor out. So that factor could be e to the power minus so j omega n minus 1 by 2 minus r plus e to the power minus j omega n minus 1 by 2 minus r. And we can just multiply over here e to the power minus j omega n minus 1 divided by 2. So we can see that these particular factors are just same. So what I can do is that I can take this one also as a group. So here it will be just then I can just put it over here. So this can be also written as in terms of cos. So h of n minus 1 upon 2 plus h of r and then 2 into cos omega n minus 1 by 2 minus r is running from 0 to minus 3 by 2 and then e to the power minus j omega n minus 1 by 2. So this is what looks like the final DTFT of the transformation of the uh, final DTFT of the impulse response of the FIR filter when the number of coefficients that we need to store is equal. Likewise, if we have n is even again by following the same symmetricity property, if we solve the DTFT equation, so there you will just get so in case of odd, you are getting some middle component. In case of even, for example, for an even case 0, 1, 2, 3. So this is a even n is equals to even. So here you can see h1, h2 could be equated, h0, h3 could be equated. So there is no middle component. Middle component. So this is when n is equals to even. So if we solve this particular equation, we'll get the same representation. Only this particular component will be zero as because there is no middle component. So I can write it as 2 r equals to 0 to n by 2 minus 1, and here n by 2 minus 1 is very trivial. You can just check the from the location of the sample components. So it will be h of r cos omega n minus 1 by 2 minus r, and then we can have the same multiplying factor, for example, minus 1 and by 2. Now, there is a problem with even number of components. So what is the problem? So when n is so n is even, then n minus 1 is odd. Therefore, n minus 1 by 2 is not integer. Therefore, phase is not integer, and fractional phase has no physical significance. So therefore, we try to work with practical phase value as because this is becoming a fraction. So therefore, we'll omit the representation of filters with n is equals to even. So thereby, it is advised to work with n equals to odd length FIR sequence. Fine. Additionally, there are some rules also associated with the FIR systems. So let us consider the FIR system as 0 at location A, then at the reciprocal location, we'll get another 0. That means at 1 upon A, we'll get another 0. And if and the provided that A is real, and if A is complex, so this comes from the linearity property, linear phase linearity property in particular. And if A is complex, then there should be a star 0 location. So that means there should be a complex conjugate operation as well as there should be a reciprocal operation. So in general, if we have a 0 at A, followed by that, I will get 1 upon A location. Additionally, as because we have considered that A is general, very general number. So let us consider the general number to be a complex number. So there should be a star. And again, as I'm getting a star, I should get a reciprocal component also again. So there could be an a star conjugate. So therefore, the 0 location could be A, 1 upon A star, and 1 upon A star. In the case of FIR phase filter, FIR filters, the 0 location could be 1, the 0 location could be A, 1 upon A star, and 1 upon A star. Followed by that, we have some filter structures also. For example, direct from structures, direct from structures. Direct from structures, let us, we have already talked about FIR filters. So let's just move to IIR structures. So as I already have told that IIR filters are related, output is related with the previous outputs, present input, and the previous input representation. So let me just write the equation and it will be clear to you. So n minus 1 and then AP y of n minus p, and x of n, b naught x of n, then b1 x of n minus 1, and then bq x of n minus q. So this is the present input, this is the past input, this is the past output. So this is what an IIR structure looks like. Now, given an IIR structure, let us consider we have a very simple IIR structure, yz upon xz. If I take z transform in both the sides, then I'm considering 3 coefficients. So b naught, b1, z inverse, b2, z power minus 2. And similarly, it will be 1 plus a1 z inverse, a2 z to the power minus 2, and a3 z to the power minus 3. Okay. Now, for this particular operation, what could be the structure of the filter that we have to visit? So we need to see what is direct from structures. So I can write it as YC is equals to XC multiplied B naught, B1 Z inverse, B2 Z to the power minus 2 minus it would be yz, then a1 z inverse, a2 z to the power minus 2, a3 z to the power minus 3. So this is what it looks like. Now let's start drawing the filter structure. So let's consider this x of n, and it is initially multiplied with b naught. So there is a multiplier with b naught, then there is a z to the power minus 1 component, and then there is b1, then again there is z to the power minus 1, and then again you have b2. Then you are adding these with adder. So here you will get the output. Okay. Now let us consider this is your y of n. So y of n is multiplied with some delay, and then there is, so this is the delay, and then minus a1. So I'm absorbing minus 1 inside. So again it would be set to the power minus 1 and multiplied with a2 minus a2. Then it will be set to the power minus 3 and multiplied with minus a3. And then we can take summation. That means we'll be using adders. So this is where you will get this particular output, and this is where we have to negate these two. So at this particular side it will be plus, this particular side it will be plus. So this is how the direct form of filter looks like. But the main problem is that we need lots of hardware resources, like the requirement of adder and multipliers are uh, requirement of adder is too much. So as far as hardware or resource uh, utilization is being concerned, we need to always think about uh, low resource utilization. So therefore, if I use some adders unnecessarily, so there is no meaning of using that particular hardware. To and if you try to reduce the number of hardware, so it will effectively reduce the number of reduce the complexity of the system, as well as the the over usage of hardware resources will also be linked. So to limit that particular hardware resource thing, we need to visit what is called direct form 2. So in case of direct form 2, we'll be able to see that the requirement of hardware resource will drastically drop. So how can we get the direct form 2? So x yz by xc, we can consider an intermediate transfer function representation vz by xz, and let us consider yz by vz is basically the denominator part. So that is what 1 plus a naught z to the power minus 1, a1 z to the power minus 1, and a2 z to the power minus 2. And bz by xz is basically the numerator. So numerator will be b naught, b1 z to the power minus 1, b2 z to the power minus 2. Okay. So bz, I can write it as xz minus a1 z to the power minus 1 vz minus a2 z to the power minus 2 vz minus a3 z to the power minus 3 vz. So it will look like so 1, 2, 3. So this is the governing equation. So I can consider input xn somewhere over here, and let us consider we have a vn. So Vn will be passed through a delay z to the power minus 1. Again, it will be passed through a delay z to the power minus 1. Again, it will pass through another delay that is z to the power minus 1. So this will lead to V. This will lead to Vn into z to the power minus 3 at this particular location. And then we can tap the outputs from each of the path. Then we'll be having some multipliers. Over here, it could be A1, A2, A3, and I'm absorbing the negative signs over here. And then, okay, so here could be plus also. That's because I have absorbed the minus sign initially itself. So thereafter, we'll be using the adders. So we'll go over here, and then here we have a xn representation. So we'll connect this over here, and this is the representation of this particular path. Now we are done with the this particular equation. Now we need to bother about the numerator part. So for numerator part, what we can do is that we can just multiply the p naught coefficient over here. Then we can take from this particular location b1. From this particular location, I can use a multiplier of b2, and then we can use adders to get your y. So therefore, we can see that initially we were using unnecessarily 2 to 3 adders more. However, over here we can see that the requirement of adders has been reduced drastically. So this is the necessity of direct control. So there are several other forms also, like cascaded forms of filters. So in case of cascaded forms, the main uh, theorem is like, so the h of n, or let us consider the h of z. I can write it as h0, h1 z to the power minus 1, h2 z to the power minus 1. So this is the general representation. I can factorize this whole thing into first order components. Let us consider I am taking some magnitude value, some constant out from this particular uh, general Z transmit sequence, and then I can factorize it in terms of like 1 minus A naught Z to the power minus 1, 1 minus A1 Z to the power minus 1, likewise. Multiplication, all are multiplied. So that means this particular is represented as H1Z, this is H2Z, this could be HNZ. So I can employ H1Z, H2Z likewise, and dot dot HNZ. So this is your XN and this is your YN. So that means all these filters are connected in a cascaded fashion. Similarly, we can also factorize these things in partial fractions also. So let us consider 1 minus AZ inverse. Then let me just consider the factors are same. Constant factors are same. 1 minus A1Z inverse, A2Z inverse, likewise. So in this particular fashion, this particular representation is called parallel uh, form. So in case of parallel form, you have x of n, and then you are using 1 upon 1 minus a1 z inverse, which is let us consider h on z, and then you are multiplying with a, and then you are using h2 of z, then again multiplying with a, and then you are using an adder over here to get the output. So here you can see that the input is processed in two particular paths, and those two particular paths in parallel with each other. So this form is called parallel form representation of filters. So we have cascaded form, we have direct form 1, 2, and we have the parallel form also. So in this manner, we can represent the filters, specifically IIR filters are represented in these particular forms. And as far as the FIR filter is concerned, in case of FIR filter also, we can use the what we call the cascaded form. You'll see that cascaded form is very frequently used in case of FIR filters. Now, let us just move to some questions which are actually related to week 6 quiz. So the first question states that X80 is an analog signal comprising two square pulses, locate strength 1. That means the amplitude is 1. Located in the interval of 0 to 1 and 3 to 4. And X80 can be written as UT minus 1, UT minus 3, and UT minus 4. So I can write it as X80 is equals to UT minus 1, UT minus 3, and UT minus 2. So this signal actually looks like this: 0 to 1 and then 3 to 4. So this is what X80 looks like. Now there is a composite operation. So first operation is what? First operation is delay by 1. So XA t minus 1 will be delaying the signal. So it will be 1, 2, and then 4 and 5. And thereafter we have XA 2t minus 1. That means scaling of time. Scaling of time here we can see we in the first class itself. I had told you that x of alpha t. Alpha could be less than 1. Alpha could be greater than 1. In case of alpha less than 1, the signal will be dilated or expanded. More precisely, it is expanded. And if alpha is greater than 1, then compression. So here we can see alpha is 2. That means alpha is greater than 1, and the signals will be compressed. So the width of this particular, so the amplitude is 1 in both the cases. Here also amplitude is 1 in both the cases. However, with a multiplication of 2, that means scaling of time with 2 will basically reduce the pulse width by half. Therefore, each points will be divided by 2. So it will be 1, and then it will be 2 and 5 by 2. So the time range is basically, so these are two disjoint square pulses. So we can consider that the locations could be written as half comma 1 and then union of 2 comma 5 by 2. So therefore option C would be your correct answer for this particular question. And similarly, let us go for the next question. So in case of next question, we have a signal YAT is XAT convolved with XAT minus 4 and XAT minus 2. And it is given that XAT is UT minus UT minus 2. So let us just draw how XAT looks like. So XAT is lying between 0 to 1, and this is a pulse. Now, given this particular pulse, we need to solve this convolution operation. So XAT minus 4. From the first class, we have already told that a signal XT, if it is convolved with delta T minus T, it will be what? X of t minus t. So by that logic, I can write it as xat convolved with delta t minus 4. So which will effectively lead it to xat minus 4. And similarly, xa t minus 10 will be xat convolved with delta t minus 10. Therefore, if I just plug this formulations over here, so it will be xat convolved with xat convolved delta t minus 4, xat convolved delta t minus 10. So thereby xat convolution delta t minus 4, delta t minus 10. So by the convolution law, I can write it as xst, xat. I will evaluate this first, and then I will evaluate xt minus 4 by delta t minus 4, delta t minus 10. So let us consider this will effectively give you HAT. So HAT convolution with delta t minus 4, delta t minus 10. So it will give you HA t minus 4, HA t minus 10. So if we know what is HAT, then obviously we can actually comment about the final output, what is YAT. So HAT is basically convolution of XAT with itself. XAT convolution XAT. So graphically, it is convolution between these two signals. So I can write XAT as UT minus UT minus 1 convolution UT minus UT minus 1. So UT convolution with UT minus UT convolution with UT minus 1 minus UT minus 1 convolution with UT, and finally plus UT minus 1 convolution with UT minus 1. So if we convolve by unit step function with itself, we'll get a ramp signal RFT, followed by these two are basically the same representation. So I can write it as 2 into R of t minus 1 plus 2 into R of t minus 2. As because we have the components minus 1 and minus 1, so these two will be added. So I will do t minus 2. Now I need to see what is the range of this particular H of HAT. Then only I will be able to comment about what H8 t minus 4 looks like and what H8 t minus 10 looks like. So for that H8t, let us consider this is the origin. So at 0th position, it is going, it is a ramp signal with slope 1. At first location, so this is at first location. So the uh, here the slope is 1 and here the slope is minus 2. So slope is 1 and at position t equals to 1. So initially the slope was 1 and here we are seeing that the slope is minus 2. So therefore the total contribution of slope is initially it was 1 and then it is minus 2. So it is effectively minus 1. So over here it will fall down with minus 1 slope. And then at position 2, what is the overall slope contribution? So initially it was 1, then it was minus 2, and then it is sorry. So here it will be just R of t minus 2. So the contribution of total contribution is 1 minus 2 plus 1. So that means at 2 from 2, the contribution of slope is 0. That means this will die down. So effectively your signal is just a triangular wave shape where the t is lying from 0 to 2. So you can use the bracket also, close bracket also. Now this is what h of t looks like. Now we need to comment about what h of a t minus 4 its range. So its range would be, as it is basically delayed by an amount of 4. So the t range will go to 4 to 6. This will go to 4 and this will go to 6. Similarly, h8 t minus 10. What it will do? It will take the 0th location to 10th position and second location to the 12th position. So the locations are T4 to 6 and 10 to 12. And as because the locations are disjoint, so again I can uh, write the overall yn will have the ranges of output starting from 4 to 6 union with 10 to 12. So T is, so it will be, it will not be a square wave. It will not be a square wave, as because we are taking the convolution between two unit step signals. The output is a triangular wave. So this is 0. This peak is coming at 1, and then the signal ends at position 2. So thereby this is a triangular signal. So these particular initial options will be nullified. Now triangular signals. Now we need to see that what is the time range. So this is not, because 10 to 12 is the final answer. So option B is the final answer for this particular question. So with this, we have covered ample amount of questions and theoretical recaps for week 6 content. So if you have any further queries, you can just unmute yourself and ask. So I hope there are no further questions. So we can stop the session over here. Let me just stop recording the session and sharing the screen as well.